Thanks for everyone coming. My name is Joel Bernstein, and I am a senior data engineer at Lucidworks. And I'm also a Lucene Solr committer and PMC member. And I'm here to talk today about mathematical modeling with Apache Solr. So for today's agenda, we're going to talk about math expressions, give an introduction to it. We're going to discuss a couple of different model types, and then we're going to go through the process of training a regression model, assessing the regression model, and then doing some prediction and anomaly detection with the model that we've trained. Math expressions is basically it's a language, a mathematics language that runs inside of Solr Cloud. And it's an integration between Apache Commons Math and Solr. And so the main design of it is to be kind of a fast, interactive mathematics, analysis of data sets. And it's a subset of streaming expressions, which means that you can provide data to math expressions by using any streaming expression that you want to use. And I'm not sure if people are familiar with streaming expressions, but there's a pretty large set of techniques for pulling data out of Solr that you can then use to present or analytics on top of. And in this table below is the current coverage, and this has been growing pretty significantly. So I think I presented on this last year, and I think there's maybe 50 functions in it. And this year there's about 250 functions. And it covers a lot of areas. It's broad compared to some of the other topics we see here, which are very heavily based towards machine learning. In this package, machine learning is just a small part of it. So there's things like statistics and probability and simulations and linear regression and computational geometry and machine learning. And this is going to continue to get broader and also continue to get deeper. So each category will get more functions as the year goes on. So I would, going to continue working on this. One of the, major areas this year we're going to work on is machine learning. So we're going to, make that a much deeper package. And I think I'm trying to think if there's another major area. There's also going to be a lot of stuff going on with text analysis. So NLP, things like that this year. So when I came to Lucidworks 2 months ago, this was one of the reasons I came, which was to kind of bring this in and start working with it with the data science team to get more kind of like well-rounded set of skills working on these functions, and also to figure out kind of what to do with visualization with it. So the other thing that we should know is that everything here actually is in Solr now. So there's nothing here that's like, you will be in the future. So you can actually run all these things now. So today we're going to talk about statistical modeling, and we're going to talk about two of the most commonly used statistical models. So we're going to do some regression modeling, and regression modeling, for people who aren't familiar with it, is predicting numeric values. And we're going to work with probability distributions, and only a little bit, but they are both very widely used models out in the real world. The support for regression in math expressions right now is what you see on the screen. So we support linear and nonlinear regression. And so simple linear regression, which is just a bivariate regression, and we have a multivariate regression, multivariate linear. And then we've got several nonlinear regressions. We have something called lowest regression, which is bivariate, and it's robust, so it's robust to outliers. And it's used often for time series modeling. There's polynomial curve fitting, which is also bivariate curve fitting, somewhat like lowest regression, but usually you fit fewer curves with it. There's harmonic curve fitting, which is sine wave modeling, which can be very useful also in time series. There's Gaussian curve fitting, which is used to fit a Gaussian peak, which you will often see used for doing things like fitting a histogram to a normal distribution. And then there's KNN regression, and KNN regression is our, at this point, only multivariate nonlinear regression, and it's extremely flexible. It's robust to outliers. It's distance-based, so you can do regression on things that you wouldn't expect to be able to do because you can change the distance algorithms. And it's just quite a nice regression tool. And probability distributions are also included with math expressions. And so I describe it very simply as just statistical models of probability, which is kind of a vague description. We'll get into a little bit of detail with it. In the real world, it's used to do things like model risk, perform simulations, particularly things like Monte Carlo simulations. They are natural outlier detectors, and we're going to use it today for that purpose. And math expressions supports a good number of commonly used probability distributions, so you can just start them up and use them to solve various problems you have. And today we're going to look particularly at the normal distribution, which has an important tie to regression models. So we're going to kind of explore that tie and use it to basically do anomaly detection with it. And there's a picture here which is normal distribution for people who haven't seen one before, but I suspect everybody has. And it's just a curve that has, it's a balanced curve where there's balance on both sides of the mean. Okay, so we have a section coming up about training a model, and this section is, we're going to train a very simple model. But what we're going to do throughout this whole stuff is a repeatable process that you can do to train any regression model in Solr. And so even though we're doing the simplest one, we're going to, you could take this and do, multivariate, nonlinear regression with it as well, using the same techniques. And we're going to do this using math expressions. So all this is done with Solr. And so we're going to give it a little bit of use case so that we can have a reason for doing a model. And so let's say that we have a website and we want to detect unusual slowness on the network. And what we're going to end up doing is we're going to use simple linear regression to look at log files, basically. And we're going to look at the file sizes in each log record and the response time for each log record. And we're going to build a regression model to basically predict responses based on file size. And then we're going to use that to actually find anomalies. So to start things off, we're going to do some random sampling. And this is kind of like, you can look at this as kind of an interactive experience between you and Solr and your data. And the random function is a streaming expression, and we call it that because it actually streams data out of Solr. So I don't necessarily call this a math expression, but it's used to feed data to math expressions. And the function is called random, and in this example right here, it is searching collection 1, and it's searching for all the records in collection 1. So basically, you can give it a query, and it will subset whatever is in that data set, and you'll get random samples from a subset of a collection. And we're bringing back 2 fields because we're going to do a simple regression, and it's bringing back the file size field and the response field, and they're both doubles. And then we're going to bring back 5 rows. And the main reason we're just doing 5 rows is we just want to see the data, because remember, we're kind of interactively building up our model. And it comes back with a set of documents that look like, kind of like what will come back with the Solr query. So you have tuples with name value pairs, and you see you've got a file size and response for each one, and they both have numeric data attached to it, which are the values that we're going to be working with. So we're going to continue to build up our expression, and we're going to set a variable. So math expressions support variables, and the way that you set variables, there is a function called let. And the let expression, you can think of that as that inside of the let expression, you're going to write a little program. And so there's the let expression here, and then the next thing after it you see is samples, and that's our variable. And then we have our random sample, and we're going to set those 5 random samples to this variable. And once that's done, it's in memory at that point. And it returns, it's supposed to return samples, but it says sample here, but it returns a variable attached to the samples themselves. So it looks very much the same, except it's responded with that it's attached to the variable. So once that's done, we can start working with the data and getting it into vectors. So all math expressions.
When will that
that gets evaluated on the spot. So right there, those 5 random samples went into memory. So, and that's why, this system is designed for random sampling. So the types of samples that you could pull from this in sub-second time for a query like this would be 150,000 if you wanted to get work like that. And so you'll find that if you're doing analysis like this, you get diminishing returns pretty quickly on sample size. Like your models will be the same, on like 20,000 samples as they would be with 5,000. So we're going to vectorize the data because all of math expressions work on vectors and matrices. So we actually can't work with this format. So what we're going to do is we're going to move the first set of data, which is the file sizes into a vector. And the way we do that is with the call function. So it stands for column. And what it does is it takes a list of tuples, and that's what the samples variable is here. And that's the first parameter. And the second parameter is the column of data that we're going to move out of it. So we're going to take the file sizes out of it, and we're going to set it to a variable called file sizes. And when that's done, we've got a variable that, so one more thing about the let expression is it returns the last variable that's been evaluated by default. So in this case, it returns the file size vector with the values in it. And notice at this point that it's no longer tuples, it's a vector of numbers, which we can start to operate on. Next step, we're going to vectorize the responses using the same exact technique. And now we have the responses. And now we're going to take the next step. So we're going to plot. Now I'm going to bring up Michael Suzuki, who is the author of a tool called Sunplot, which is using to show plotting here. And at Lucidworks, we're going to be working on plotting solutions soon, very soon. But in this case, the reason why we're plotting is now that we have these vectors of data, it would be nice to know what they look like to decide what model to pick, because you don't know if you want to get some kind of intuition about whether it's linear or nonlinear. So that's one place to start. And the way that we're going to do that is that we're going to sort the vectors by the file sizes, and we're going to keep them paired together. And that way what we're going to see is that as the file sizes grow, what happens to the response times? So does it grow as well? Does it grow linearly? Is there some other nonlinear shape to it? And so there's a function called pair sort, and pair sort sorts 2 vectors together, and it sorts them based on the first vector. So it sorts them based on file sizes, but it ties them together. So when you're done, it returns 2 vectors to you in the form of a matrix. So that variable sorted vectors is actually a matrix, and the first row of the matrix is the file sizes vector, and the second row is the responses vector. So, and they'll be sorted by file size from the ascending order. And the next line, we're going to take the second vector from that matrix using the row at function. So the row at function takes a row from a matrix and returns the vector from it. In this case, it's returning the one that's indexed at 1, and I'm just calling that the variable sorted responses. So I've just got a vector of sorted responses by file size, and then we're going to plot. And this plot function is doing something, it's creating an output that Sunplot understands. So it's not doing anything special right now, just creating a particular output. And then we're giving it a type of scatter, and we're giving it a y-axis of sorted responses. And this is what Sunplot looks like when you do that. And so you can see from left to right, as the file sizes are getting bigger, the response times plotted on the y-axis also get bigger. So your intuition at this point is that, yeah, there is some kind of relationship. First of all, it's not just random. So it tends to be getting bigger. And if you look at that, if you were to put a line down the middle of it, a straight line, you could model that pretty well with linear regression. So at that point, we're saying, okay, we're going to, after taking a look at this, our intuition says we're going to do simple linear regression, and that's what we're going to do. And it's as simple as calling one more function. So here we're taking random samples, but we've moved it up to 5,000 because we're going to have a bigger random sample set to take. And we're vectorizing both the file sizes and responses. And then we're calling the function regress, which just does linear regression and takes two parameters. So it takes the predictor parameters, predictor vector as the first parameter, and the outcomes as the second parameter, and it returns to you a simple regression model. And that model looks like this. And so it gives you model diagnostics right onto the screen. And attached to those diagnostics is actually the actual model that can do predictions. But you can look at this model diagnostics and understand quite a bit about your regression model. And we're only going to look at one of these because you can get into some pretty heavy statistical jargon with this stuff. But R squared tells you the percent of variability that the predictor value has for the outcome. And in this case, we have 82% variability is described by the predictor variable. So we're saying, okay, it looks like our model has some potential of being decent at this point. And because we think it's decent, we're going to cache it, okay, because we're going to use it later. So there is a function called putCache, and putCache takes two parameters to start with. It takes a workspace and a key. So the workspace is models, and the key is regression 1. That's what we're actually going to call the model. And the workspace is so that you can have multiple users working with caches at once on the same server, or you can have multiple applications working with on the same server without overriding each other's cache. And then we're just going to stick the model in the cache. And when it goes into the cache, it goes into memory. So this is something that we're also probably going to change a little bit at Lucidworks. We're probably going to harden that so it goes to the blob store or it goes somewhere where it's going to be actually used in more than one memory space. But right now, it goes into memory. And once it's there, it's cached and ready to use. So we're not sure we want to use it yet, but we at least know that it's good enough to be worth caching. Okay, so we have a model, and it was that simple. So this, how many lines of code did it take? It took 5 lines of code. We have a model. So it doesn't get a lot easier than that. And even for more trickier models, still will take very little amount of work to do. So this stuff can be done quickly, and the response time on this is going to be, I don't think actually it has it here, but it's going to be like 10 milliseconds or something like that to build that model with this many records. So if we were to build it with 100,000 samples, then it would be somewhere around a second probably to build the model. Okay, so the next step is to assess the model, because in the real world, you don't just take a model and put it out and hope it works. So with regression models, there are techniques for knowing whether the model is going to work for you and be consistent. And we're not going to use those diagnostics very much because they're only available to us for linear regression. And what we're going to look at today is steps that we can do to validate any of our models. So we can validate any nonlinear model using this technique. And the technique is to use the residuals. And so I'll describe what the residuals are soon in the next couple slides. But we're going to calculate the residuals. We're going to describe the residuals statistically. We're going to do a normality test of the residuals. We're going to plot the residuals looking for something called homoscedasticity. And then we're going to model the residuals with a probability distribution. Okay, so what are residuals? So in regression modeling, the residuals are the difference between the actual value and the predicted value. So basically, it's the error in your model. And once you have your residuals calculated, you can use that as a data set of its own, and you can do all kinds of assessments on that data set. And that's like the key core technique to working with regression models. And one of the things that we're going to do with it is we're going to model those residuals with a probability distribution. And we are going to, what we're hoping for, in pretty much every regression model you build, what you're hoping for is errors, so residuals that are normally distributed and homoscedastic. And in the real world, you might not get that exactly, but that's what you're shooting for. And if you don't get it, then you keep working to try to get it. So you might want to change your model from linear to nonlinear. You might want to do some type of transformation on the data to try to get it that way. But anyway, that's the goal, really, of building the model. And we'll talk about how we assess that. So the first step is that we're going to do predictions with the model. And it's quite easy to do predictions. So we're going to take a different random sample, here. And this time we're only going to work with 500 because we're going to just use these as, as validating the model, and we're going to plot them as well. So we downsample to 500 to do that. And we vectorize the file sizes and response times again. And here we have get cache, which returns the model. So it says get cache, you give it the workspace, you give it the model name, in this case regression 1, and you've got your regression model and you're up and running. And then, just as simple as that, you call predict. And you pass it the model, and predict knows what to do with every single regression model, as well as many other types of things that we have in math expressions. So it knows what to do with the simple linear regression model. And what you're going to give it to, as the second one, is you're going to give it the predictor values, which is in this case our random sample of file sizes. And what that's going to return is a vector of predictions. So basically at this point the predictions variable here is set to the vector of predicted values for this random sample. And it looks like that. So we put our model to work that quickly. And this response time is literally like, it's like nothing, it's like 0, maybe that fast. And then we're going to calculate the residuals. So we have one more line here, we make the predictions, and then to get the residuals, we need to take the actual response times and subtract the predictions. So remember, for this data set, we have the actual response times already in the set, the responses field. And so we're going to subtract the predictions from the responses using a function called EBE subtract, which stands for element by element subtract, which is part of our vector math library. And we're just going to subtract it, and it does, it returns a vector of residuals. And those residuals is what we want. So that's the whole goal of doing the prediction and then, doing the subtraction here. So, and at that point, once we've done this little, quick bit of math, we're in great shape to start looking at the residuals vector, and it looks like this. So sometimes the residuals are going to be negative, sometimes they're going to be positive, and we'll discuss what that means. But each one of those represents the error for a particular prediction. Okay, so the next step we're going to do is we're going to statistically describe the residuals using the describe function. And this does, statistical analysis of the residuals. And basically, we're putting that to the variable summary, which looks like this. So this is summary statistics of the residuals. And what's important to us here, first of all, is the mean. So we see the mean is close to 0, and that's a good sign, because when you put a line through a scatter plot, there are going to be some errors above it and some errors below it. You would want your mean to be balanced and close to 0. And then you've got the standard deviation, which gives you the spread of error. Okay, so then we're going to take our summary statistics and we're going to model our residuals using probability distributions, in this case, a normal distribution. So in the way that we're going to do that is that we have our summary data here, and we need to take two values from it. We need to take the standard deviation and the mean, and we're going to create a normal distribution from it. And the way we're going to get those values is using the getValue function, which takes a tuple and returns the value attached to a key. So in this case, we're saying get value from the summary tuple and return the mean for the first one. And for the second one, we're saying get value and return the standard deviation. And we're basically creating our normal distribution from that. And this normal distribution variable is another model. It's a probability distribution. So once we have a probability distribution, we can do a test to see if it's normal or not. And the test that we're going to do is called the KS test. So, and what the KS test does, it takes a reference distribution, in this case the normal distribution with the mean and standard deviation, and we're going to test it against a vector of numbers, in this case the residuals themselves, and it's going to come back and tell us whether or not that vector matched the distribution. So it's like a pretty foolproof actually as far as knowing whether or not this thing's a normal distribution. And it comes back with what's called a p-value, which is a significance test for it. And in this case, a p-value of 0.65 basically says it is a normal distribution. If it was a p-value of 0.05 or below, typically you discard it and say it's not a normal distribution. And the reason why it's important that it's normal distribution is that when you have a normal distribution, it makes certain things with anomaly detection very easy, and other follow-on math. So if it wasn't a normal distribution, it wouldn't be the end of the world. You could go back and transform the data to get it to be a normal distribution, things like that. But it's, in this case, it turned out to be a perfect one because I planned it that way. Okay, so the next thing we're going to do is we're going to cache the normal distribution. So we have two models in cache. So we're putting in cache the models. We're putting it back in the model, into the workspace. And we're naming it dist1, and we're putting the normal distribution in. And so now we've got a probability distribution describing our residuals, and we've got a regression model. And from that, we are ready to take one more step. We're going to do a residual plot using sunplot again. And so let's talk quickly about homoscedasticity. I'm not sure anyone knows what that term here is. Anyone know what it means? Okay. So basically what you want to do is you want to make sure that your model has consistent variance in the errors. So if you have a model that has different prediction errors at different places basically different predictions. So as the predictions go up or something like that, if the variance spreads in the errors, you can't trust the model. So what you need to do is you need to take a quick look at the residuals and see if that's the case. And we're going to pair sort again, because that's another technique for looking at this stuff, is we're going to sort by the predictions, and we're going to pair sort with the residuals. So what you're going to get is you're going to get a vector of residuals that are what you would see as the predictions go up. So as the predictions get higher, what do your residuals look like? And again, we get our matrix, you get the ROAD, and we're going to plot the sorted residuals, and it looks like this. So what's nice about this plot is that, so on the x-axis, it would be the predictions getting larger, and on the y-axis, it's the residuals, it's the error. And in this case, you see the error is perfectly smooth, or it's very even across all of it. And so remember that the mean of the error was close to 0, and you had errors below and above and below it. And so we have a homoscedastic model, or homoscedastic errors, which is great, because now we're ready to put the model into production and start using it. So how do we put this model in production? So it's already in production because it's in the cache. So you could actually, if you want, you can move it to another area, like you could say, get it from the one spot of the cache and put it in production cache, and it would be 1 second and it's published. And it's out there. Like I said, at Lucidworks, we're going to harden that, so probably it goes across the whole cloud, so it will be across everything. But once it's there, you can just start asking it questions or start processing data, doing anomaly detection, and making predictions. So let's do some predictions with it. And so the first thing you can do with it is that, Solr understands this statement just as it is. If you say get cache, the models in regression 1, it's going to return to you the model. So there's our model gotten from the cache. And then we can just give it a function, predict. It understands this. And so you can call get cache. It will return the model as the first parameter to predict. And then we're giving it a value to predict, a single value. So it's going to give us a prediction for a file size of 10,000. So you could stick this on the network and just fire stuff at it. And just fire the questions at it as much as you want. It's going to come back in 0 milliseconds, and you can hit it an awful lot. And you don't have to run this on nodes that have data. You could just have this on nodes. So it could be extremely reliable and just essentially run forever under extremely high load. And it will come back with an answer. It'll give you a prediction, which is useful. It may not be so useful in this little use case we're having here, but let's say you're building models for high-speed trading where you're trying to forecast the next tick. You could be having this thing sitting up their network, producing, output for you, predictions for you. And we can do streaming prediction. So this is where it gets kind of clever. So the let expression also allows you to end itself, not with a variable, but with a stream, which means that you can set variables above it and then have a stream that recognizes those variables and puts them into scope. And so let's walk through how it works. So the let expression, the first thing we're doing is setting the variable regression model. So we're pulling the model out of the cache, and that variable is now in scope for the stream underneath of it. And let's look at what that stream is doing. So that stream is doing a search, and it's searching collection 1 for all star dot star. It's pulling back the ID and the file size. It's getting 10 rows, and it's doing a sort. And then we're wrapping that. So that's going to bring back 10 tuples with an ID and a file size. And we're wrapping that in a select statement or select expression, which is an extremely clever expression. So what it does is it goes to each tuple, and it's doing this in a stream sense, so it never runs out of memory. So you can do as much as you want with this. And it's first two things it's saying, I want to first pull out the ID field and the file size field, and I'm going to put that in the outgoing tuple. And then it's creating a new field called prediction. And it's using the predict function to make the prediction. But what's clever about this is the two variables in the predict function. Notice the first variable is regression model, which we pulled out above it. The second variable is file size D, which is coming from the tuples themselves. So the variables, as it iterates each tuple, the fields in the tuples themselves come into scope. So you have this really clever scoping going on where everything just works. And you can do this forever, without, depending on how you do this, it just, you can do billions of records this way. If you want to do large scale prediction or anomaly detection, or if you just have a very specific set you want to do. So that's one approach to this, and it will return to you, the let expression returns the tuples with the prediction looks like this. So you've got file size D, you've got prediction, and you've got the IDs. Okay? So let's do some anomaly detection. It's a little more complicated, but it's not so much more complicated. So let's, we're doing the let expression, except now we're getting two variables. We're getting the regression model, and we're getting the normal distribution out. And the normal distribution, remember, is of the residuals of the error. And what we're going to try to do here is we're going to look for error in the model that is unexpectedly high. And so instead of doing a search here, we're doing a topic. And a topic subscribes to a query. It gives you all new records. So imagine taking a topic and sticking it on top of a set of logs and just calling it over and over again, so that every time you call it, it brings back another set of new records. And it's doing that using the version stamp for every record. It does that automatically. So, and it keeps its checkpoints so it's durable. And so the topic is bringing back the fields, the ID, the file size, and the response. And then we're going to use the select on top of it. And this is a lot of fun, this one. So here we're taking the ID and the file size, and we're doing a prediction. Okay, so, and we're creating a new field called prediction. And then in the next one, we're going to use that new field. Not only can we create a new field, but we can use that new field as a variable in the next line. So we're saying subtract the actual response from the prediction, and we have a residual. And that residual can then be used on the next one. And this next one here's where you're getting your probability distribution into play. So we have a residual, which we just calculated using that subtraction, the response D from the prediction. And their cumulative probability function takes a probability distribution, in this case our normal distribution of the residuals, and you give it the residual number that you have it, and it tells you basically what's the probability that you would get that. And in this case, it says the probability that we would get something like that would be like 0.37, something like that. And so if you get a probability that's unusually high or low, then basically you can say it's an anomaly at that point and alert on it. And because your model was homoscedastic and normally distributed, these anomalies have value. They mean something. They're real. That's it. I don't know if you have time for questions. I think we might not have time for questions. So it's 3. Anybody have questions?
Yeah.
Okay, go ahead. Front row.
Yeah, I mean, just quickly, are you competing with Jupyter and Python and R? I mean, I'm a data scientist.
So at this point, I wouldn't say competing. What I'd say is if you are a Solr user or a Lucidworks customer and you have a lot of data in that system, this will give you more value on what you have. So if by some chance this brings more people to the table outside of the Solr community, great.
So I can see this getting pretty intensive, computationally intensive. Can you shard this work?
So that's a great question. So it shards in specific ways. So when you, let's talk about, it breaks down aggregation, random sampling, time series, stuff like that is spread across the cluster, pushed down and brought up. And what you get back are kind of compressed record sets. So let's say you do a time series, you're not going to get back massive amounts of time. You're going to get back some small enough set. So at this point, random sampling and compression of records is designed to give you fast results on the perfect result set rather than crunching massive result sets like Spark. It's just a different way to look at the world. And whether or not people prefer one or the other, I don't know, but it has a place because even if you want to do the whole result set Spark, you might want to do this first to investigate. So say, okay, let me sample and see what's here before I even bother, crunching a 2-hour, model on it. Yep.
Could you describe a little bit more about how random works?
Sure. So this is so I don't know if anybody was here for Kevin's talk before me, but he was using random as well to do his work. But what it is there's something in Solr called a random sort field. And really what it's doing is it's doing a random sort. And it takes the doc ID and it hashes it. And then it comes up with a value. And then the way that Solr actually does things, it has a priority queue that very quickly sorts. And so things will randomly sort. So if you say, give me the top 300, it will give you the top 300 that randomly sorted that way. And the way the random function works is it gives it a new seed each time, and that seed is taken into account when it generates the random sort, basically.
Does it have to evaluate, or does it have to match essentially all the documents?
Yeah, but Solr does that for every query anyway. So when you do a score, or when you do think of it's still lighter weight than scoring.
Okay.
Yeah, so because if you score, you have to do a bunch of calculations. For this, there's a hash involved, but the hash is pretty quick. Anything else? I think he had his hand up right there, behind you.
You still switch up to training and test sets?
I basically did in this example. It was kind of hard to tell, but the second set of random samples that I did was not the same one that I did to actually train the model.
Are they overlapping?
No, because it depends how big your data set is. So let's say you had let's say you had a log set with millions of documents in it. The first random sample that I built a set from was 5,000, and the next one was 500. It's unlikely they would overlap. Yeah.
So we have big data set, right?
Mm-hmm.
Million records, and we want to use a string regression to get some closer to near-time prediction. And how can we make it fast? Because when I was creating this string expression, I was recognition about how linear I see in the slowness.
Well, the thing is that you have to use the right expressions. So if you go to the export handler and export everything, it's going to take however long it takes to sort and export everything. You only use the export handler in one situation, ever, and that's for joins. That's it. If you're not doing joins, don't use the export handler.
So for example, if we need to use the join, but
Okay, if you have to use the joins, and you have to put up with the performance. So there's nothing, you can't get it for free. So if you're going to do a distributed join with millions of records, it's going to take however long it takes to do. And you can make it go faster because you can put that in parallel, and you can go in parallel with it, but still, it's not going to be sub-second likely.
But for example, even before it was taking 30 seconds, maybe we can cut it to 5 seconds.
It will take what it takes. So if you're going to do distributed joins, we can talk about how you scale up distributed joins, but if you're really going to do that and try to make it fast, you need a lot of hardware. So don't try to do distributed joins with lots of data on a single server.
Sometimes you need it, so it's not as you can avoid based on what
We see it a lot. We see a lot of people who are upset that distributed joins aren't faster. Definitely.
I was seeing that in the Solr documentation, they use a parallel function.
Yes.
And you can configure can make work normally.
Yes.
You can make cut the processing time,
Yes.
percentage.
Yes, that should work.
But how do we configure them? What is it? Need a Solr
Talk to me later about that, because that's a bigger discussion, but it's very easy to do. Like, it's just a matter of like having your collection set up a certain way and then sending the query in a certain way. But when I say big though, I mean having something like, you know, 10 to 20 shards and 5 to 10 replicas. You really want, if you're going to be doing distributed joins, you have to have a lot of power behind it. And it also depends on, there are a lot of things that would depend on how fast that's going to be for you. But, and you know, how many documents you're trying to join and how many keys you're sorting on and things like that.
That last slide, I missed what you said. Those are the outliers that you were saying that were possibly a problem.
Oh, here?
Yeah, I did.
So that was the cumulative probability. I didn't describe what that function really means.
Yeah,
But,
I kind of missed your conclusion there.
oh, the conclusion was they're not outliers. But yeah, they're not outliers, no. The cumulative probability, what it does, it says, in this case, the residual, what it's telling you is what is the probability of everything below that residual. So in this case, the residual, the first one, the residual is 0.6, and it's saying that the cumulative probability, everything below that was 0.37.
So how does that relate to like the standard deviation?
So you could do this with standard deviations as well.
I was in aerospace for 8 years.
Yep.
We typically reject points based on standard deviation,
Yeah.
like 2.5 as
Yeah.
standard deviation or something like that.
You could do it just like that too.
It's really kind of, your choice.
It is.
Yeah.
So the other way to do it is with z-scores. So you take it and so if you have a normal distribution, you compute the z-score, which is basically the number of standard deviations from the mean, and that can also give you your thing. And if you have a normal distribution in your residuals, then that is meaningful. If you don't have a normal distribution in the mean, or normal distribution in the residuals, then the z-score and standard deviation is not meaningful. So that's the thing. So that's when you would use these probability distributions. You can do what's called an empirical distribution, which will give you a meaningful probability result, even if you're not using a normal distribution. So that's why I used it here.
It probably gets pretty interesting using other models.
Oh, yeah. Yeah. It's very cool. I mean, so right here, what we looked at was probably 15 functions altogether, and there are, 250 functions covering a lot of stuff. And every release, there's 15 more coming in. And, so it's just growing and it's more interesting. And the math, this I would consider foundational, all the rest.
You have multivariate, nonlinear?
Yeah, I was showed that in the beginning. That's our KNN regression, nonlinear. Yeah, so we have, KNN regression's amazing. The things that you can model with it are just.
Multivariate.
So I was doing KNN regression with latitude, longitude vectors. So basically, bringing up latitude, longitude, getting them into vectors, and then basically using Haversine meters as the distance measure. And then you can do things like, predict housing prices based on nearest neighbor things like that. But not only can you predict the housing prices, you can build the model, get the residuals for it, and see how good your model is for predicting housing prices. So it's not just like, slamming out there, here's what it is. Yeah.
So can you adding more custom functions to it?
Yeah. So yourself, you're saying. Yeah, so you can. So you write the functions in Java, and you plug them in the Solr config, and then they just come into play with all the rest of the functions. So you just have to know the API. So every contribution that gets done with this is pretty much done that way. You write a custom function, we contribute it, and then we hard code it into Solr, but you can also plug it in.
Joe wouldn't be adding 50 of these a month if they're hard to run, if they're complicated to put in.
Well, the reason why it's so fast to do is because I'm not doing the math. So if I was doing the math, it would not get done. But so because I'm using Apache Commons Math, it gets done very quickly. But there's another library called the SMILE library, which is a very comprehensive machine learning library, which we're going to do next. And so we're going to see like a whole bunch of machine learning stuff. So where you have 250 functions over the whole thing right now, you may see another 200 of just machine learning coming in. All right.